Hello everyone, and welcome to the third video in our Class 9 time series of instructional videos for organic chemistry. In this video, we'll be looking at another example where we have the chlorination of propane versus the bromination of propane that we looked at previously. So again, one could think about chlorinating propane and forming either 1-chloropropane or 2-chloropropane and HCl. Statistically, we might expect a distribution of 75% of the 1-chloropropane and 25% of the 2-chloropropane because there are 8 total protons on this molecule. 2 of those 8, or 25%, are the secondary carbon protons, either of which would lead to this product, and then 6 of the 8 are the primary carbon protons, so 75% of the protons would lead to this product were they extracted. Experimentally, of course, we actually do observe some selectivity. We prefer abstracting secondary hydrogens over primary. We get a 57% yield of the 2-chloropropane and only a 43% yield of the 1-chloropropane. This is less selective than what we observed for radical bromination. So again, let's try a relative reactivity ratio for secondary hydrogen versus a primary hydrogen for chlorination. What we would do is we would take our 57% experimental value, divide it by the number of protons that could lead to this product, so that's 2, and compare that to the 43% of the observed 1-chloropropane normalized to the number of primary hydrogens, which is 6, and so our ratio turns out to be about 4 to 1. So we expect a secondary hydrogen to be 4 times more reactive than the primary hydrogen for the purposes of radical chlorination. So this reaction is much less selective than radical bromination for secondary versus primary hydrogen atoms. Why is this reaction less selective? Well, first, it's exothermic versus radical bromination's endothermic reactions. So chlorine abstracting primary hydrogen in this elementary step, our change in enthalpy is -2 kcals per mole, whereas radical chlorine abstracting a secondary hydrogen to give our secondary radical in HCl, our change in enthalpy is -4.5 kcals per mole. So remember the Hammond postulate. An exothermic reaction looks more like the reactants than products. Both paths have early transition states, and the transition state has little alkyl radical character. So here's our energy versus reaction coordinate diagram. You can see for the pathway where our radical chlorine reacts with propane and leads to a secondary propyl radical, isopropyl radical, our activation energy is only 0.5 kcals per mole, whereas the pathway where that chlorine radical reacts with the primary hydrogen, our activation energy is 1 kcals per mole. And here are our changes in enthalpy of 2 kcals per mole for our first elementary step that we considered chlorine abstracting a primary hydrogen versus 4.5 kcals per mole for that radical chlorine abstracting a secondary hydrogen. Okay, so what about radical fluorination? Following the periodic trend, selectivity decreasing from bromine to chlorine, fluorine is even less selective than chlorine since the reaction is even more exothermic, and this is because of the strength of the hydrofluoric acid bond and the carbon-fluorine bonds that are formed. In practice, chemists rarely do radical fluorinations unless they are fluorinating the entire molecule. Also, in practice, chemists rarely do radical iodinations because all the bonds are weak, and we saw, at least in the radical iodination of methane that we had endothermic, a completely endothermic change in the enthalpy for the reaction. So a good summary example could be the radical halogenation of 2-methylpropane. So what we have is primary and a tertiary proton. So we have a total of 10 hydrogen atoms. 9 of them are primary and 1 of them is tertiary. So statistically, we would expect 90% of a product where we substituted one of those 9 primary hydrogens for a halogen, and then 10% of the product where we substituted the tertiary hydrogen for the halogen, and of course a couple of equivalents of HX. So for fluorination, radical fluorination, like we said, fluorination displays little selectivity. Our relative reactivity of a tertiary to a primary hydrogen is about 1.5. You can see it's very close to statistical. We get 86% of our 1-fluoro-2-methyl-propane and only 14% of our 2-fluoro-2-methylpropane. So very close to that 10%. How about radical chlorination? Well, our relative reactivity of a tertiary hydrogen to a primary hydrogen is 5 to 1. So we get 36% of our 2-chloro-2-methylpropane and 64% of our 1-chloro-2-methylpropane. How about bromination? Well, we get almost all 2-bromo-2-methylpropane and very little of our 1-bromo-2-methylpropane, because our relative reactivity of a tertiary hydrogen to a primary hydrogen is like 1700 to 1. So that's a pretty good summary example. I hope you will all be able to do that kind of reaction analysis for radical reactions. I think one more page and then that concludes our video and our videos for this Class 9 time. In fact, according to Table 3.6, the relative reactivities for different types of proton atoms, hydrogen atoms for halogenation. Here we go. For radical bromination, tertiary is 1700, secondary 80, primary 1. Chlorination 5 to 4 to 1, fluorination 1.4 to 1.2 to 1. So bromination is the most selective. Organic chemists like selectivity. Fluorination shows little selectivity. So unless you want to fluorinate your entire molecule, you got to add fluorine in a different way. Chlorination is still performed, but usually only on substrates having one type of hydrogen, so we don't have to worry about the less selectivity issue that chlorination poses in the radical mechanism. So chlorination of methane or chlorination of cyclohexane, I mean, there's only one type of secondary hydrogen in this molecule. So that pretty much concludes our Class 9 series of talks, and I will see you for Class 10.